All right, so our next addition is an important one. We've, at this next step, added 25 milliliters of our sodium hydroxide, which we determined to be the amount of sodium hydroxide we would need to add in order to reach our equivalence point. So once again, we're going to start with our strong acid, strong base titration. Again, recognize that we are reacting our hydroxide ion with the hydronium ion in solution to form water. And in the weak acid, we're reacting our hydroxide ion with that formic acid molecule to form water and its conjugate base. Now, for our strong acid, strong base titration, at the equivalence point, the strong base has completely neutralized all of the hydronium ion from the strong acid. Therefore, the only source of hydronium ions is going to be from the water. That's the only thing present other than the neutral salt that is formed at the equivalence point. The only source of hydronium ions then is from the self-ionization of water, which is going to be 1 times 10 to the negative 7, and therefore the pH of our strong acid, strong base titration at the equivalence point is going to be a pH of 7. Now, let's take a look at the weak acid and strong base titration. We've added 25 milliliters of sodium hydroxide, which is equivalent to 0.0025 moles of sodium hydroxide that we added. Because of the one-to-one relationship that it has with the formic acid molecule, it's also the amount of the formic acid that was consumed. So we've used up now or reacted all of the formic acid molecules. However, it's important to recognize that we've also produced 0.00250 moles of our formate ion, or the conjugate base. So recognize now that at the equivalence point for the weak acid strong base, it's not just water, but also our conjugate base. And so to determine the pH at the equivalence point in the weak acid strong base titration, it's simply a weak base equilibrium problem. Recognize, though, that this amount of moles of your conjugate base is going to be in a new volume, because you have your initial 25 milliliters of the acid that you started with plus the 25 milliliters of the sodium hydroxide that you added, for a total of 50 milliliters. So the concentration of your formate ion or your conjugate base is 0.0500 molar. So in order to solve for the pH of a weak base, it's simply a matter of writing your equilibrium expression and setting up an ice table. Our initial concentration of that formate ion, 0.0500 molar. Again, the change in concentration will be represented based on the stoichiometry. Our equilibrium concentrations are then set up. However, before we solve this, some important things to keep in mind. We're talking now about a base, and we're going to be solving for a hydroxide ion concentration. So a couple of things before we solve this. One, we first need to know what the Kb value is for this weak base. And so we can do that using the relationship between Ka, Kb, and Kw. If you rearrange that expression to solve for Kb, you simply need to then plug in the value for Ka that was given to us initially at the beginning of the problem, using the Kw constant to get a Kb that is 5.6 times 10 to the negative 11. Once we have a value for Kb, we can just plug it into the Kb expression and solve for our hydroxide ion concentration. Again, we're going to make the x's small approximation to make our life a little bit easier here, and we determine the hydroxide ion concentration to be 1.7 times 10 to the negative 6. If you plug that into the formula for POH, we get a POH of this solution to be 5.77. But recognize we're looking for a pH, so we also need to understand and remember the relationship between pH and POH, and then plug in our POH value to get a pH of the solution to be 8.23. So a strong acid, strong base titration will have a equivalence point that occurs at a pH of 7. A weak acid, strong base titration is going to have an equivalence point in the basic range, because as your weak acid is neutralized, it's forming water and a weak base. All right, now to complete our calculations here, we're going to take a look at what happens once we've added 30 milliliters of our strong base. So now we're past the equivalence point, and it really just becomes a matter of an excess reactant type of situation. If we take a look at the strong acid, strong base, again, our hydroxide ion no longer has any hydronium ion to react with. We've used all of it up. Likewise, in the weak acid, strong base titration, our hydroxide has completely used up the formic acid molecules. And so at this point, when you solve for the number of moles of sodium hydroxide added, we get 0.00300 moles of sodium hydroxide that was added, but we only had 0.0025 moles of the other reactant for that strong base to react with. So in each example, we're going to have 0.00050 moles of hydroxide ions that are in excess. All right, so once you've gone past the equivalence point, it's simply a matter of determining the concentration of that excess hydroxide ion that's in solution. So we've got that 0.000500 moles of hydroxide ion that is in excess. The total volume, again, you've got to watch out, make sure that you recalculate the new volume based on the amount of base that you've added to get the new concentration of your hydroxide ion in solution. For the weak acid strong base, we're just going to use the concentration of the hydroxide ion like we did in the strong acid strong base. At this point, the hydroxide ions from the strong base are completely overwhelming the weak base that is in solution. And so we solve first for the POH, which is just the negative log of the hydroxide ion concentration. In each example, this calculation is going to be the same. We have the same concentration of hydroxide ion in excess. So our POH is 2.04 in both cases. Remember, the relationship between pH and POH is 14. To solve for a pH of the solution after the addition of 30 milliliters to be in each case 11.96. So to take a look at our titration curves, we've gone past the equivalence point. We're now clearly in the basic range here due to the excess amount of hydroxide ions in solution. Okay, and as you look at your notes there, we continue to add the sodium hydroxide, and the calculations for these are done the exact same way as the calculations done at 30 milliliters. Again, once you're past the equivalence point, it's just a matter of recognizing that you've got an excess reactant type of situation. Now, you're given those values in your notes, but recognize for both the strong acid strong base and the weak acid strong base, those values are going to be the same. And as you compare your final titration curves, again, recognize that your initial pH of the strong acid is going to be a little lower than your initial pH of the weak acid due to the fact that your strong acid has complete ionization where your weak acid does not. Keep in mind that on the weak acid, we're going to take a look at that and focus on the half equivalence point in which the pH is equal to the pKa of your weak acid. Your equivalence points in the strong acid strong base titration is going to be at a pH of 7 or a neutral pH, but in a weak acid strong base titration, it's going to be in the basic range. And then beyond the equivalence point, you've got a situation where you've just got excess hydroxide ion.